Chapter 3 on Differentiation, Section 3.2, the derivative as a function. Previously, we have learned that if we take a function and find the slope of the line tangent to that curve, so you have this line tangent to the curve at, say, some generic x value, then we'll say that the slope of the line is the derivative at that particular x. So in general, for any x, for a particular function, if we take the limit of f of x plus h minus f of x, whole thing divided by h approaches 0, what we derive is, or what we obtain is a slope function. So the derivative in itself is a function. And for notation purposes, there are different ways to denote the derivative of y equal to f of x. Sometimes we denote it as f prime of x, or sometimes it's y prime. It's also defined as dy by dx, or d by dx of the function f of x, or df by dx, and even we use the notation capital D of f of x with a subscript small x, with a subscript small x, to mean that we are taking the derivative with respect to the variable x. So the slope of the line tangent to the curve y equal to f of x at the point A, say it's just a generic point A, f of A is equal to m, which is f prime at A, or other notations that were used in the previous slide. Let's take, for example, if y is equal to x squared and its derivative is 2x, the slope of the line tangent to the curve, say at x equal to 2, would be 2 times 2, which is equal to 4. So if we were to graph the function y is equal to x squared, we get a parabola that slopes upward right there, and the corresponding derivative function is a line with slope 2. And what this says, what this is that for every point on the graph of y equal to x squared, there is a corresponding tangent line to the curve at that point, and we record the slope, and that corresponding slope would be the y value for that particular x right here. So say if x is equal to -1, the slope of the line tangent to the curve at x equal to -1 is -2. So it'll be recorded right here. If x is equal to -1, then y is equal to -2 right there. See, x equal to -1, your y is -2. So that -2 is the slope of the line tangent to the curve at y equal to the curve of y equal to x squared, and its slope is -2. What is the slope of the line tangent to y equal to x squared when x is equal to 0? It's a horizontal line. And what is the slope of a horizontal line? The slope is 0. So notice that at x equal to 0, the slope of the line tangent to the curve is 0. So we plot the point 0, 0. That's why the line of the graph of the slope function passed through the origin, because x0, y0 is part of the graph. And notice that to the right, or for x is greater than 0, all the slopes of the lines tangent to the curve will have positive slopes. That's why the graph now of your derivative function is in the first quadrant, because all the slopes for every x, say x equal to 1, the slope of the line tangent to the curve is 2. We know that because of plugging in x equal to 1, and 2 times 1 is 2. So this just shows you the relationship between the slope function and the original function y equal to f of x. Here, let's go ahead and see why the graph of the derivative for the original function y equal to f of x behaves this way. Let's take, for example, the point on the graph of y equal to f of x, say at x equal to negative 1.8. And we take the slope of the line of this tangent line, and it's equal to positive 4, because if you check out the point at x equal to negative 1.8, that's where the y is 4. So the slope of this tangent line is 4, and where we have a 0 slope, that means the curve or the graph of the slope function will have y equal to 0. So it passes through the x-axis where x is equal to negative 1.4, okay, right there. And if we continue now on to the curve of y equal to f of x, notice that all of these slopes are negative. Negative slope, negative slope, negative slope, etc. All the way up to 1.4, right there, where it changes slope again. So from negative 1.4 all the way to 1.4, the slopes are negative, which shows here that the curve of the derivative function is below the y-axis because they're all negative slopes. And once again, it changes. It becomes positive, so the graph of the derivative function would cross the x-axis, because from negative to positive it will have to hit a 0, and that occurs when the slope is 0. That means when the curve of the original function changes direction from negative slopes of the tangent lines, and then of course before it becomes positive, it'll go through 0 because it will have a horizontal tangent line, therefore the slope is 0. So when x there is equal to 1.4, the slope is 0, so you graph the corresponding derivative function at 1.40, and there it is. And if we go past 1.4, say 1.8, okay, the slope now becomes positive again. So you have a y value occurring above the x-axis. So the graph now appears above the x-axis past 1.4. Now, let's go ahead and work on this problem that we left off last Wednesday, where we want to match the graphs of these functions from 27 through 30 and see which one matches the corresponding derivative function. Okay, well, we just looked at the previous slide when we looked at a parabola, and we said that the derivative function is a line that passes through the origin. So here the slopes are of the lines tangent to the curve would be negative, 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 and then you get a 0 slope, which means the y values for the corresponding slope function would have negative y's, and then it becomes 0, and then positive slope, positive slope, positive slope. So that means that 27 will match with letter the graph of B. Okay, so 27 matches with graph of B. Now let's look at number 28. In number 28, notice that the slopes of the lines tangent to this curve will all be positive because they are all sloping upwards, all the tangent lines, until you get a 0 slope right here, and then it continues on to be positive slope, positive slope. So what do you think would match the graph of number 28? Remember, positive slope, positive slope, positive slope, 0, positive, positive slope, etc. That means that the best candidate for number 28 would be letter A, because they are all positive values except at the origin when y prime is equal to 0. Okay, So that means number 28 matches letter A. So this matches the graph of number 28 for its original function. Okay, let's look at number 29. I'm going to graph the tangent lines there, okay? Because where the lines are tangent to the curve and they are horizontal, that means the derivative function would have a y value equal to 0. So if that's a 0, we'll find where there are 1, 2, 3, 4, 5 times that it passes, that the slope is 0 means you have 1, 2, 3, 4, and 5. And I think this does match, letter D does match the graph of number 29 as its derivative function, because the slope here is positive, which means the graph would be positive right there because that defines the slope, and then it's 0. And then from here, from between two slopes, okay, between two horizontal slopes, we have a decreasing function, so the slopes of the tangent lines are all negative, 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 etc. So here it stays negative. These are the slopes of the graph of the slopes of the tangent lines, okay, and so on. And then between this point and here, these slopes are all positive. Indeed, between these two horizontal tangent lines, we see that the slopes of the lines tangent to the curve are all positive. There's a slope, there's a tangent line with a positive slope, etc. So all these would have positive slopes, which means these are the corresponding y values of the derivative function, and so on and so forth. So between the origin at x equal to 0 and another x right there, so that's at x equal to 0 and another x right there, where we have a zero slope for the tangent line, 0 slope for the tangent line. All of these slopes of the lines tangent to the curve are negative, and notice that these y values correspond to the slopes of the lines tangent to the curve. And then from here on all the way here, between two zeros of slopes, that's slope equal to 0, and that's that part. This is a slope 0, and that's that part. And between these 2 points of the x, we see that the lines tangent to the curve are all having slopes positive. So see, it occurs above the x-axis because the values of y prime here are all positive. So D matches with 29. And naturally, since this is the last choice, 30, the graph of number 30 matches with letter C. And let's just see why that is the case. Here, the slopes of the lines tangent to the curve are negative. Negative slope, until you reach a horizontal tangent line with slope 0. So where that you have a 0 slope for the tangent line, that's where the curve of the derivative function will pass through, will intersect or cross the x-axis, because that's when y value is 0. The y coordinate is 0. So that corresponds to the slope. And then from here on up to 0, the slopes are all positive. So from here to 0, the slopes or the y values of the derivative function is positive. And then from here to here, it changes direction. It's going down, which means if I take a look at all the slopes of the lines tangent to the curve, between here and here, they're all negative slope, and then 0 slope. So there's your 0 slope. And then to the right, okay, to the right here, or rather, to the right, these are all positive slopes. So the y values of the derivative function will be above the x-axis. So I hope that helps you match the derivative function and the original function with how we've looked at all these 4 examples or 4 problems.